All right, so here we are. This is 126, and we're down here. So it's going to be debugging today and Ollie debug next time. And so let's, 5G, current witchcraft. Yeah, I think hacking is actually the current witchcraft. When people think hackers can do anything, they have magic powers, they can get anywhere and stuff like that, and they're very, very afraid of them. But anyway, that's why I think even our current level of madness needs to be put in a bit of historical perspective. Anyway, you may notice I skipped a few chapters. I think this is an easier way to do it. The book went straight into disassembly, and disassembly is the most difficult part of the class, and I think it's much easier if you learn debugging first. So, a disassembler just shows you the program, and then you can read it and try to figure it out, but it doesn't run. You just have to learn how to read the code, which is difficult, but debuggers let you run the program and watch what it does. And they also show you not just the program, but they show you the memory that's changed as the program runs and the registry values that change. So, Bigfoot shows, yeah. All right, and so you can stop the program at any point, and you can change things. So there's two basic debuggers, Ollie debug and a later version of it called Immunity debugger, which is essentially the same thing. And this does user mode debugging only. It's only for user mode software like anything you would launch from the start button or the desktop. It is not for kernel debugging, the heart of the operating system. For that, you must use WinDebug, which is Microsoft's product. And it is probably a much more powerful debugger, but it is much, much harder to use. So we're going to start with Ollie debug to make it as easy as possible. IDA Pro, the disassembler, does have a debugger, but it's also not very good, not very easy to use. But Ollie debug is very popular because it makes it easy to understand what's going on at the binary level in programs. Now, developers typically use a source debugger, which means they can see something like their C++ source code and run it and stop on a line of source code and look at the variables mentioned in the source code and all that, and that's the best way to use debuggers for their original purpose, which is to help you find the bugs in your own code. And that's fine for developers, but for malware analysts, we never have that. You never have the source code, unless there are very small number of cases where the developers actually made a mistake and left the source code in there, but normally it's removed. So we have the more difficult problem of trying to debug a binary without the source code. And that is, you never do have anything very easy to read. You have to learn how to read assembly code, to some extent anyway. So when an app crashes, you'll see Windows pop up this box, this program has stopped working, would you like to close it or debug it or check online? And so it will tell you the module that crashed and something about the exception code and so on. And if you try to debug it, then it will open the WinDebug. Yeah, the quizzes for each chapter are due before the chapter, yes. I switched to that years ago, the recommendation of other teachers. That way students have to read through the book first. And the end result is they learn more. The Chapter 8 PDF is behind a paywall. Just a moment while I research this. Chapter 8? Oh, yeah, the PDF just not linked there. You can see the slides right here. It's just if you want to get to the PDF, you have to make an account here. And I can put a link to it later so you can get the PDF. But thanks for telling me. That's good. Yep. That's right. I added these PDF links for most of them, but somehow I missed Chapter 8. I can add it later. But you can see the slides right here. It's just if you want to download it in a PDF, I don't think you have to pay. You just have to make an account. This is just the SlideShare, and that's a free Microsoft product these days. Anyway, thanks for reminding me. I'll try and remember to put up a link to that PDF. All right. Good. Anyway, so there's kernel mode and user mode debugging, which I mentioned. Now, in user mode debugging, you debug a program that runs from the start button, and you're debugging one executable, and it runs in its own limited memory region, separated from other executables by the operating system. So if the program stops or crashes, it doesn't freeze the operating system. It just freezes that one program. Now, kernel mode debugging is where you're going to be putting breakpoints in and stopping and modifying the code in the kernel of the operating system, which is the part that touches the hardware that's used by every application. So if you were to put in a breakpoint and stop the kernel, the machine would be frozen and dead. So the old-fashioned way was to have two computers connected by serial cable. And one would be controlling the other, so it could stop the other, so you could examine the kernel and then tell it to go again. And that's the old-fashioned way to do it, with two machines connected. You would go into the advanced boot options and something like Windows 7, and you would turn on Enable Debugging Mode. And then your machine would know it was going to be debugged through a serial cable, and on you go. Now, this was not very popular because you needed two physical machines, and because the serial cables have long been extinct and did not even exist in the hardware anymore, so you'd have to go somehow simulate them or get some old expansion cards to get these old serial cables. And so Microsoft developed easier ways to do it. But anyway, the other thing, print screen would then cause a blue screen of death, freezing it after you turned on debug mode, and that was bad for students who were trying to get screen prints. Anyway, the new trick. This first new trick that occurred out was Mark Russinovich. Mark Russinovich, who is the administrator of Azure, he made this live KD tool that takes a memory dump, like after a crash, and then lets you examine the memory dump. So you can view the kernel on a running machine without a second machine. You cannot stop the kernel or put in a breakpoint, but you can view it, and that gives you a lot of value. So that's one way to do it. That's what he did. It fooled the debugger into thinking it's looking at a crash dump and present them with data from the kernel. So anyway, that's the way, and that's essentially what happens with the new WinDebug preview that we're using in Windows 10 in some of the projects. It does this sort of automatically and nicely. So you can view the kernel in one Windows 10 machine without having a second Windows 10 machine connected to it. And by the way, this is a great video. B-sides, where Joe McRae, who is a really great guy, explains how to use OllyDebug for complete beginners, which helped inspire me to write my malware exploit development class, demystifying that stuff and making it a lot easier to understand. All right, so let's take a look at a Kahoot. I should have favorites, and there we are, 8A. That's good. Okay. I'll give it a few more seconds. All right. All right. So what techniques requires two computers connected together? Okay, that's the kernel mode debugging. Good. All right, what technique is almost never used with malware? That's it. You can't do source level debugging. The only person that can do that is the malware author who has the source code. All right, what technique shows you assembly code but doesn't let you run it? right, that's disassembly. All right, if you get the blue screen of death, how should you debug it? Okay, you're doing kernel debugging, and that was, in fact, if you pay Microsoft a support fee, you can email the crash dump to Microsoft, and they will debug it and figure out why your stuff crashed. All right. All right, those look like real initials. That person will have to tell me who they are if they care about points. And that's a real name. Good. All right. All right. So good. We're on track. All right. So using a debugger. One thing you can do is launch the debugger first. Oh, I see. Someone's giving me a name there. Good. Make a note of that. All right. All right. Good. So you can launch the debugger and then open a program in the debugger and run it, and then it will load the program and stop immediately without running it, so you can examine it before you start it running. The other thing you can do is you can attach the debugger to a running process. That's another way to do it. If you have, all right, something like a background process, something you don't want to launch inside the debugger. All right, you can then single step through the program. You can do step, one assembly language instruction at a time, and sometimes that's useful if you can get near to an interesting point, like a crash or something else you want to examine. But if you don't know where you want to be, there are thousands and thousands of machine language instructions, and single stepping through it all is too much bother. So for example, here is some code that will decode something. It's going to do XOR location EDI with a fixed value. So it's going to put some kind of memory address in EDI. Then it's going to increment EDI. So it XORs it, increments it, and then does some kind of loop to go back here. So it's going to decrypt something by XORing every byte with 9C. So what you might want to just single step through it, step, and then watch it as this area of memory gradually becomes clear. That's an easy way to do it. If you don't have too many steps to go through. Now, you can do step over or step into. If you are at a certain level in the program, like you're in the main routine, and then it calls another routine, like print. Now, you could jump into the print routine and then stop and debug that. Or maybe you don't care about the print routine, you just want to keep moving at the same level through the main routine, because that's called stepping over. Stepping over would mean if it calls a subroutine, run the whole subroutine and return, and then resume. That's stepping over. So you zip through all the instructions below this level and come back to this level. Therefore, you don't see the details of what happens in there. You might miss something. In fact, it might never return from that routine because there's something like a crash down there. So stepping over might never end. But normally, stepping over is a way to stay in the code you want, and the most common reason you do it is because you've got userland code that was written by the developer of this program, and usually you're looking for bugs in that code. Eventually, it's going to call the kernel, the Microsoft API, and normally you don't want to bother looking for bugs in the Microsoft API because Microsoft is pretty smart, and their code is pretty clean, and they patch it a lot, and usually you don't want to be looking inside the Microsoft code for bugs. So you'd rather just step over the steps that go into the Microsoft software and get back to the software written by a more amateur developer. Anyway, that's commonly how I do it. So you can step into a call and move down a level, or you can step over to stay at the current level you're at. All right. And you can put breakpoints, which are extremely useful. If you find a spot in the program where something interesting happens, you can put a breakpoint and run down to there. So for example, here it's going to call something, but this is self-modifying code. It's going to call an address that is calculated in EAX. So I don't know where it's going. So I could put a breakpoint here and run down to there and then look at what EAX is, and then I'd find out where it's going. That's the sort of thing you might want to do. All right. Here's something that calculates a file name. It's going to take a .txt, and then it's going to somehow calculate more words and gradually build a file name. And so here, it's calling create file W with all these values which are on the stack, and here it's calculating these things to put on the stack. So again, you'd put a breakpoint here, so it does all this calculation, and then at this point, before it calls this, you can look on the stack and see what file name it built. This is common in malware, that it has a command and control center that is a random domain name, but it's not really random. It has some kind of pattern, and the malware author knows what domain names are coming up, and they can purchase them in time to take control of the malware. But you can't just read them with strings or anything. You'd have to use something like this, like breakpoints, to have it generate these names and see what they are. All right, so here's what WinDebug looks like. It's one of these strange things Microsoft does sometimes where it's really a command line tool, but they put it in a window just to give you a headache. So it's got a command line here where you're typing commands, and then the results go up here. But anyway, you can put a breakpoint into a function. Here they put a breakpoint on create file W, and it ran to that point and stopped, hitting a breakpoint and showing the values there. Here's EAX and EBX and ECX and so on. So it does have the same information that you'd see in a debugger like OllyDebug, but it's a whole lot more difficult to use. Everything has to be done with little abbreviated commands you type down here. It's friendlier for scripting though. So, it's more powerful for an advanced user, but more difficult for a beginning user. All right. And for example, if your malware has encrypted data, which is very common, then you just have to find where it uses it and put a breakpoint after it decrypts it, and then you can see what it is. So here's an example. It's going to make a function call it's going to get data from someplace, then it's going to call a function to encrypt it, so you just put a breakpoint here. At this point, it's ready to encrypt the data. The unencrypted data is just sitting on the stack. You can find it. If you can find which call calls the encrypted data, which is a little harder than you might at first think. And I've mentioned before, when I'm debugging things like PHP malware, I've often made a mistake trying to understand what the routines do and run parts of it that I didn't really want to run. So you always want to work in a virtual machine whenever you're working with malware. It's very easy to make a mistake and activate the malicious part of the malware. So here's OllyDebug, which is a nice graphics tool, and you got the registers over here on the right. You have the assembly code here. You have a place here you can dump any kind of values you want in hex, and you have the stack down here. And it's all very nice and pretty and easy to use, and we'll use it quite a lot in this class. All right, so when you make a breakpoint, there are 3 different kinds of breakpoints. The software execution breakpoint is the most common one. What you do to make a software execution breakpoint is the memory contains a valid assembly language instruction, really a machine language instruction, and the debugger changes 1 byte of what's in the memory with the byte CC. CC is an interrupt 3, and that causes the program to stop and return control to the debugger. So it modifies the memory image of the program. That's how it works. And this is very easy to do. It's very effective. And of course, when you remove the breakpoint or you move past it, it will take the right value and put it back in that byte to move ahead. So that's what's going on. So if you look at it, this is supposed to be a push, EBP, which is supposed to be a 55. But when you put a breakpoint there, the debugger puts a CC there instead. So it will actually be an interrupt 3 when it hits there. And then when you press something like step over or continue, it will replace it with the right value and move forward. So that's how it works. The debugger is doing what we talked about first, code replacement. It's changing the memory image in RAM of a program while it runs. All right, now the problem is sometimes this won't work. For example, if your code reads the memory and does something like do a checksum to see if it's been modified, it will find that 1 byte is no longer right. So sometimes a software execution breakpoint will not succeed. Although I don't think I've ever needed anything else in anything I've done, but I haven't done all the most complicated stuff. So when that fails, you have alternatives. Hardware execution breakpoints are designed to put breaks in programs without modifying them at all, so there are special debug registers. You can have 4 addresses of breakpoints, and therefore it will stop whenever it gets to that location. either accessing that location or executing code at that location, on read, write, or both. That's what these hardware breakpoints are for, but there's only 4 of them. You can't set a lot of them at a time, but they operate without modifying the code. Now, unfortunately, you can have anti-debugging measures in your malware. It can modify these DR registers to turn off those breakpoints or modify them. Now, there is a attempt to prevent that attack in a detect flag in one of the registers, and it catches a move instruction that would change the contents, but there are other instructions besides move that can be used to override it, and it won't detect them. So this is just the way it always is. The cops get bigger guns, and the crooks get bigger guns, and the cops get bigger guns, you know. But that's the state of the battle back and forth between debugging and anti-debugging. All right, and then there's conditional breakpoints, which are just implemented in the software of the debugger itself, typically Python. And what these do is you might want to set a breakpoint on a function, but then you find out that function is called hundreds of times, and you only want to see it when it's called under certain other conditions. So that's what a conditional breakpoint is. You're going to put a breakpoint on a function, but you only want it to really stop if a certain parameter is being passed in here. So this is implemented by the debugger as a software breakpoint. It puts in a CC type software breakpoint, and it stops, and then it examines to see if it should just automatically continue or not. And if the condition you want is not satisfied, it recontinues. So in an automated way, it will zip through. Now that will be much slower than running at full speed all the way through, but it's a lot faster than you having to manually look at every break and decide this isn't the one I want, this isn't the one I want, running past them. All right, so it takes much longer than ordinary instructions, but you know, it's an option. And again, I've never had to do that either, but I haven't analyzed anything very complicated. All right, let's take a look at some more Cahoots. We are done with 8A. We're down to 8B. All right. By the way, if you're late on anything like a quiz, just do it anyway. That's okay. We only take a couple points off when things are late. The only reason I have deadlines at all is just to keep people moving. All right, we'll wait a few more seconds. All right. All right, what breakpoint uses interrupt 3? All right, that's the common type software execution. All right, which kind of breakpoint slows down your program? All right, those are conditional breakpoints because you keep leaving the fast machine language and going out to Python for the debugger to decide if the condition is met. All right, what's the most common breakpoint? Oh, that's software execution. Good. All right. And which one might cause you to skip important functionality? That's step over. You run a whole bunch of code and supposedly come back and you don't really know what happened inside there. All right. All right, good. I know who these people are. I know who that is. Good. Okay. Good. All right, so we got enough time to do the last section of this. All right, so exceptions. If you do something like a divide by zero, or you attempt to execute kernel mode instructions while you're in user mode, or go to a memory address that is not reserved for use by your program, that will trigger an exception. You try to do anything you're not allowed to do. And an exception is raised, and then the program will do various different things depending on what type of exception it is. So breakpoints also generate exceptions. All right. So a first chance exception is when something has happened, and the first thing it does is just hand it to the debugger and say, okay, do you want to handle this? Maybe this was just a breakpoint or something harmless. Then the debugger will take action. It doesn't want to stop the program or anything. That's the first chance. Now the debugger can handle the exception by just posting up a message on the screen and letting the user do something, or you can hit a key like F9, which will cause the debugger to pass the exception back to the program, so now the program will try to handle it. Now, professional software developers will write exception handlers in their code. Let's say, if something bad happens, I write a handler what to do. If they don't, the operating system itself will have some ability to handle exceptions. It will do something like pop up a box and say, your program has stopped, please tell Microsoft about this problem. That's what would happen if the program handles it. So the debugger, you hand it back to the program, then the program will attempt to handle it. And if the program doesn't handle it, then Windows will handle it. All right, if that goes to the second chance, the debugger is given a second chance. And if that happens, that means the program did not find an exception handler that would handle this exception. And now the program is about to crash, and the debugger gets a second chance. All right. And so if you ignore a second chance, then it's going to crash and pop up a box and stop everything. All right. Stop that application. Not going to stop the entire machine unless you're debugging the kernel, but it'll stop that application. So int3 is the one we talk about mostly. That's a software breakpoint. It just means I want the program to stop, but it doesn't mean anything is wrong. I'm stopping it because the user wanted to put a breakpoint there and examine the situation. And if you do the single step we talked about before, that's really implemented with the CC. A single step, what the debugger actually does is put a breakpoint on the next instruction and run, and then it breaks. That's how it implements it. All right. There's also something called a trap flag in the flags register that will do this, execute one instruction and then generate an exception automatically. All right. Another kind of exception is memory access violation. This is what happens a lot in buffer overflows. You put in something like a lot of capital A's. Some of those end up in the instruction pointer, and then it tries to execute memory at that location, but that location is not a valid memory location. That hardware is not, it either doesn't exist in the hardware, or it exists but it's not allocated for use for this program. So that's a memory access violation. You attempted to access a location that you are not allowed to access. All right, violating privilege rules is very common. For example, you try to run a kernel mode instruction in user mode, or you try to execute code in a region of memory that is in March non-executable, which is supported by all modern motherboards since like 2010 or even earlier. And that's a security restriction on the use of memory. This memory region is not allowed to have instructions, and if you try to execute instructions, it will cause an exception. All right. So you can get a list of exceptions out there. Here's 3, the breakpoint, non-maskable interrupt, debug, exception, divide by zero, and there's a lot of them. So it'll send these codes up and then let the exception handlers in either your program or the operating system take action based on this code. All right, so if you want to modify what happens with a debugger, you can change things. You can stop with a breakpoint, and you can change the value of registers, change the instruction pointer, change the instructions in memory, and make the program run differently. So you can put a breakpoint at the call, change the instruction pointer to go after it, or anything like that. That's the whole point of using a debugger. You can modify how a program runs. You could run a function directly without finding the conditions in which the main code would use it. You could just prepare the parameters, call the function, and then get the results that come out of it. All right, and so in practice, what you typically do is you, here's one of the cases that's extremely common. In Russia, we are under constant attack by the Russians. In fact, I was just preparing a instant response training video for the last few days, and I put up an Azure server, and immediately the Russians started trying to break into it. There's automated processes that immediately try to connect to every Azure server you put up. If you connect RDP directly to the internet, there'll immediately be brute force attacks, and these ones I got were coming from Russia. And this is the current situation. Russian cyber criminals are encouraged by the government to attack Americans, and they're told that we will not do anything to you if you attack Americans. So most people who define, with Cowrie, I don't know, Cowrie, yeah, sure. Anytime you make any kind of public server, either if you open SSH on port 22 or RDP on 3389, you'll get it. Yeah, you're turning into a honeypot. Anyway, so so if you are a Russian criminal, you can attack American targets with impunity and steal money from them, and the government will say, that's great, do more of it. But the rules are you must not attack Russian targets. Otherwise, they'll prosecute you. So when you find malware that comes from Russia, it typically tests to see if you're Russian. This is why I actually saw a recommendation about a month ago, which sounded pretty good. If you don't want to get hit by ransomware, all you probably do is add Russian language to your Windows machine. That will stop almost all of it from running. Now, I don't know if this is really, if the bad guys haven't caught on to this, but it is a good point, because that's what they do. They typically check the language setting of a computer. And they are typically created by either criminals that live in one country and don't want to go to jail, or by military of that country. And in any case, they have target selection. So here was a piece of malware where if it detects that you have Chinese, it will do no harm. If it detects that you're English, it will just put an irritating pop-up, but their real target was apparently Japan, then it'll wipe out the whole hard drive. So it's the sort of thing that you'll find in malware. A lot of malware will check like this to decide what country you're in and decide what to do based on that basis, so the criminals that set it up can avoid committing crimes in their own country. So here's what you do. It's going to call this thing called Get System Default LCID, which is like a location identifier. I don't know exactly what it stands for, but that's the point. Something about the language set on the machine. And if you put a breakpoint here, you can see what it is. And here's what it's going to check. It'll check if it's 409, it's English, it's 411, it's Japanese, this is Indonesian, and that's Chinese. So if you don't want to bother setting up a test machine in Chinese, which would be pretty annoying if you don't speak Chinese, you could put a breakpoint here and then modify. When this returns, it's going to return with EAX equals the return value. You could have an English machine where this returns English, but you put a breakpoint here and then you change EAX to be C04. And now the program will think it's on a Chinese language machine when it isn't. So that's an example where you might want to modify the registers while debugging a program. All right, let's take a look at the last cahoots, which are here. All right, I guess we got everybody. All right, so which item handles exceptions during normal program execution? That's the structured exception handler. I realize I didn't mention this. I'm not sure it was on these slides, but it is the truth. Structured exception handler is the exception handler that coders write into their program, if they are good coders. That's your program's handler. All right. As part of why these Kahoots are extra credit, some of them are kind of unfair. And that one was a little bit unfair. All right, what exception doesn't stop code execution and can usually be ignored? That's the first chance. Something has happened. We'll give the debugger a chance to stop if you want, but normally you would let the program see if its exception handler can handle it. So you can usually ignore that one and pass it back to the program. All right, a Ring 3 process tries to access hardware directly. What happens? That's privilege violation. You attempted to execute an instruction, but you are a user-land program and you are not authorized to execute a kernel mode instruction. Ring 3 is user mode and Ring 0 is kernel mode. Rings 1 and 2 exist, but they're not used by any modern operating system. The only ones we use are Ring 3 and Ring 0. All right. The Soviet. Sock puppet, I know who that is. The Soviets not getting their points unless they come out of the closet, though. But these other people have real names and will get their points. Anyway, all right. So let me stop this recording.